Welcome to our deep dive into the system design of the Twitter Android app. In this video, we'll explore how Twitter's mobile platform is engineered for scalability, efficiency, and real-time user experience. We'll break down the architecture, key components, and workflows that make the app robust and responsive. Whether you're a developer, a tech enthusiast, or simply curious about how large-scale apps operate, this journey will reveal the secrets behind Twitter's seamless performance. Let's start by understanding the overall goals and requirements that drive the design of this popular social platform. Twitter Android app is built to deliver a rich set of features. Users can post tweets, view timelines, follow others, like and retweet content, and send direct messages. The app must handle high concurrency, ensuring millions of users can interact simultaneously without delays. Real-time updates are crucial, so users instantly see new tweets, likes, and notifications. These functional requirements shape every layer of the system, from the user interface to backend services. Let's look at how these needs translate into technical solutions throughout the app's architecture. Beyond features, Twitter's Android app must meet strict non-functional requirements. Scalability is key, supporting millions of concurrent users. Low latency ensures a real-time experience, with tweets and messages appearing instantly. High availability is a must, aiming for 99.99% uptime so users can rely on the platform. Data consistency is also critical. Likes, follows, and tweets must always reflect the latest state. These requirements drive the choice of technologies and architectural patterns, ensuring the app remains robust under heavy load. Twitter Android app follows a classic client-server model. The Android app acts as the client, communicating with an API gateway that routes requests to various microservices. This separation allows each service, such as authentication, tweets, feeds, notifications, and messaging, to scale independently. The API gateway handles load balancing, authentication, and caching, ensuring efficient and secure communication. This modular approach is essential for maintaining performance and reliability as user numbers grow. The client side, the Android app provides the user interface and manages local storage for caching. It uses Jetpack Compose for a modern, reactive UI, Room database for local data caching, and Work Manager for background synchronization. Networking is handled by libraries like Retrofit or OKHTTP, which support retry logic for reliability. Authentication is managed via Firebase Auth or JWT-based tokens, ensuring secure access. This layered approach keeps the app responsive and efficient, even with intermittent network connectivity. The API gateway is the central hub for client requests. It routes traffic to the correct microservices, handles load balancing to distribute requests evenly, and manages authentication by validating JWT tokens. Request throttling is implemented to prevent abuse, limiting excessive calls from a single user or IP. Caching is also handled here, improving response times for frequently accessed data. The API gateway's role is crucial for maintaining security, performance, and scalability across the system. Twitter's backend is powered by independent, stateless microservices. Each service is responsible for a specific domain: authentication, user management, tweets, feeds, notifications, and direct messages. This separation allows for easier scaling and maintenance. For example, the authentication service manages user login and session tokens, while the tweet service handles tweet creation, likes, retweets, and replies. The feed service generates personalized timelines, and the notification service delivers real-time alerts. Direct message service manages user-to-user chat, ensuring fast and reliable communication. Authentication service is the gatekeeper for user access. It handles login, registration, and session management using OAuth 2.0 or JWT tokens. User credentials and session tokens are stored securely in a database. This service ensures that only authorized users can access the app, protecting sensitive data and maintaining privacy. By leveraging industry-standard protocols, the authentication service provides a robust foundation for user security across the platform. User service manages profiles, followers, and following lists. It provides endpoints for retrieving profiles, following or unfollowing users, and updating user information. Relational databases like SQL are used to store user data, ensuring consistency and easy querying. This service is essential for building the social graph that powers Twitter's network, enabling users to connect and interact seamlessly. Tweet service is at the heart of Twitter's functionality. It handles tweet creation, likes, retweets, and replies. When a user posts a tweet, the service saves it in the database and publishes an event to the feed service. Endpoints are provided for creating tweets, liking, retweeting, and replying. This service ensures that user interactions are recorded and propagated efficiently, forming the core of the Twitter experience. Feed service generates personalized timelines for each user. It uses two main approaches: fan-out on write, where tweets are pushed to followers' feeds as soon as they're posted, and fan-out on read, where tweets are fetched on demand. Redis is used to cache pre-computed timelines, ensuring fast access and low latency. This service is critical for delivering the real-time experience users expect from Twitter. Notification service keeps users informed about likes, mentions, retweets, and new followers. It uses messaging queues like RabbitMQ or Kafka to ensure reliable delivery. Push notifications are sent via Firebase Cloud Messaging (FCM), providing real-time alerts directly to users' devices. This service is essential for maintaining engagement and keeping users connected to the platform. Direct message service enables real-time user-to-user chat. It uses NoSQL databases like Cassandra for fast, large-scale message storage. WebSockets are employed for live message updates, ensuring instant delivery and synchronization. This service is designed for high throughput and reliability, supporting private communication between millions of users. Twitter's backend relies on a mix of relational and NoSQL databases. Relational databases like MySQL and PostgreSQL store user information, tweets, and follower relationships. NoSQL databases such as Cassandra and DynamoDB handle real-time chat messages and notifications. In-memory databases like Redis and Memcached are used for caching timelines and rate limiting. This hybrid approach balances consistency, scalability, and performance across different types of data. Relational databases are used for structured data. The users table stores user information such as ID, name, and email. The tweets table records tweet content, timestamps, and user IDs. The followers table maps follower relationships, enabling the social graph. These tables are designed for consistency and efficient querying, forming the backbone of user and tweet management. NoSQL databases like Cassandra and DynamoDB are used for storing real-time chat messages and notifications. The messages collection holds chat data, while the notifications collection tracks alerts sent to users. These databases are optimized for high throughput and scalability, supporting the fast-paced nature of Twitter's messaging and notification systems. Memory databases like Redis and Memcached are used for caching. The feed cache stores prefetched timeline data, enabling fast timeline loading. Rate-limiting cache tracks API calls from each user or IP, preventing abuse and ensuring fair usage. These caches are essential for maintaining low latency and high performance, especially during peak traffic. When a user posts a tweet, the Android app sends an API request to the tweet service. The service saves the tweet in the tweets table, then notifies the feed service using the fan-out on write method. Followers are updated in real time and notifications are sent via the notification service. This workflow ensures that tweets are instantly visible to followers and authors are notified of engagement. To view the timeline, the Android app requests data from the feed service. The service fetches tweets from the Redis cache or queries the tweet database if not cached. Fetched tweets are displayed on the user's timeline, providing a seamless and responsive experience. This workflow leverages caching to minimize latency and maximize performance. When a user likes a tweet, the app sends an API request to the tweet service. The service updates the like count in the tweet table and triggers a notification to the tweet's author. This workflow ensures that engagement is recorded and authors are kept informed, maintaining the interactive nature of the platform. Sending a direct message involves establishing a WebSocket connection. The message is sent to the direct message service, saved in Cassandra, and delivered to the recipient in real time. This workflow is optimized for speed and reliability, supporting private conversations between users without delay. Caching is a cornerstone of Twitter's performance strategy. The feed cache stores user timelines in Redis, enabling instant timeline loading. User profile cache keeps frequently accessed profiles ready for quick retrieval. Rate-limiting cache uses Redis to track API requests, preventing abuse and ensuring fair access. These strategies collectively reduce latency and improve user experience. Support millions of users, Twitter employs several scalability techniques. Load balancing with NGINX distributes user traffic evenly across the API gateway. Rate limiting prevents abuse by restricting excessive API requests. Sharding splits large tables like tweets and messages into smaller shards, improving performance. Read-write separation uses dedicated databases for reads and writes, optimizing throughput. CDN like Cloudflare caches media files, reducing load on backend servers. Security is a top priority in Twitter's system design. JWT tokens are used for session management, ensuring secure authentication. Sensitive data like messages and passwords are encrypted, protecting user privacy. Rate limiting defends against DDoS attacks by restricting API calls. Role-based access ensures users only access their own data, maintaining integrity and confidentiality across the platform. Role-based access control is implemented to ensure users only interact with their own data. Permissions are assigned based on user roles, restricting access to sensitive information and operations. This approach enhances security and prevents unauthorized actions, maintaining trust and reliability within the platform. Load balancing is crucial for handling large volumes of user traffic. NGINX is used to distribute requests across multiple API gateway instances, preventing bottlenecks and ensuring high availability. This technique allows the system to scale horizontally, accommodating growth and maintaining performance during peak times. Rate limiting is implemented to protect the system from abuse and ensure fair usage. Redis is used to track the number of API calls from each user or IP. If limits are exceeded, requests are throttled or blocked. This strategy prevents DDoS attacks and maintains system stability, especially during high traffic periods. Sharding is used to split large tables like tweets and messages into smaller, manageable pieces. Each shard operates independently, allowing for parallel processing and improved performance. This technique is essential for scaling the system to handle millions of users and massive amounts of data. Read-write separation is implemented to optimize database performance. Separate databases are used for read and write operations, reducing contention and improving throughput. This approach allows the system to handle high volumes of data efficiently, supporting real-time updates and fast retrieval. Content Delivery Network (CDN), like Cloudflare, is used to cache media files such as images and videos. This reduces load on backend servers and speeds up content delivery to users worldwide. By distributing media across multiple locations, the CDN ensures fast and reliable access, enhancing the user experience. Data encryption is applied to sensitive information such as messages and passwords. Encryption ensures that data remains secure during transmission and storage, protecting user privacy and preventing unauthorized access. This measure is vital for maintaining trust and compliance with data protection regulations. Session management is handled using JWT tokens. These tokens are issued upon login and used to authenticate subsequent requests. By validating tokens, the system ensures that only authorized users can access protected resources. This approach provides a secure and efficient way to manage user sessions. The feed service uses two main approaches for timeline generation: fan-out on write and fan-out on read. Fan-out on write pushes tweets to followers' feeds as soon as they're posted, while fan-out on read fetches tweets on demand. Each method has its advantages, balancing real-time delivery and resource efficiency. Messaging queues like RabbitMQ and Kafka are used to deliver notifications reliably. These systems ensure that alerts for likes, mentions, and follows are sent in real time, even under heavy load. By decoupling notification delivery from other services, the system maintains responsiveness and reliability. Firebase Cloud Messaging (FCM) is used to send push notifications to Android devices. FCM provides a scalable and reliable way to keep users informed about activity on their accounts. Real-time alerts enhance engagement and ensure users never miss important updates. WebSockets are used to enable real-time messaging in direct chats. This protocol allows for instant communication between users, supporting live updates and synchronization. WebSockets are ideal for high-frequency, low-latency interactions, making them perfect for Twitter's messaging needs. Room database is used on the Android client for local caching. This allows the app to store data offline and synchronize updates in the background. By caching frequently accessed information, Room database improves app responsiveness and reduces network dependency. Work Manager is used to handle background synchronization tasks on the Android app. It ensures that data is updated even when the app is not actively in use, maintaining consistency and reliability. Work Manager is essential for keeping timelines, messages, and notifications up to date. Networking in the Android app is handled by libraries like Retrofit and OK-HTTP. These tools provide robust support for API calls, including retry logic for reliability. By abstracting network operations, they simplify development and ensure consistent communication with backend services. Twitter's backend leverages event-driven architecture for scalability and responsiveness. When a tweet is posted, an event is published to the feed service, triggering updates for followers. This approach decouples services and enables real-time propagation of changes across the platform. Maintaining data consistency is vital for Twitter's reliability. Techniques like transactional updates and eventual consistency are used to ensure that likes, follows, and tweets always reflect the latest state. This focus on consistency prevents errors and maintains user trust. High availability is achieved through redundancy and failover mechanisms. Multiple instances of services and databases are deployed, ensuring 99.99% uptime. Load balancing and automated recovery keep the platform running smoothly, even during failures or maintenance. System design can be expanded with advanced features like analytics, content moderation, and A/B testing. Machine learning can be applied for feed ranking and dynamic caching, further enhancing performance and personalization. These optimizations keep Twitter at the forefront of innovation and user engagement. Summary: the Twitter Android app system design is a showcase of scalable modular architecture. By separating microservices, leveraging caching, and using messaging queues, the platform supports millions of users with high performance and reliability. Security, scalability, and real-time responsiveness are at the core of every decision. As technology evolves, Twitter's architecture is ready to adapt and grow, ensuring a seamless experience for users worldwide. Thank you for joining this exploration of Twitter's Android system design. We've seen how thoughtful architecture, modern technologies, and robust workflows come together to create a platform that's scalable, secure, and engaging. As Twitter continues to innovate, its system design will evolve to meet new challenges and opportunities. Stay tuned for more insights into the architecture of world-class apps.